Okay, today we're talking about linear regression models. This first lesson's not very calculator heavy. It's more about just understanding what a linear regression is and how we use it. That's homework from yesterday's lesson. Okay, so why do we make a regression line? So it's kind of a line that models the data. It looks kind of like that. You can see it's negative slope there. So it's just an easy line to kind of use that. And we make this line for purposes of prediction. In fact, when you read this equation, it says y hat equals a plus bx. Y hat means predicted value. We're using x, the explanatory variable, to predict the y variable. And so you want to think of that y as being predicted by x here. So we even like to write that variable as the predicted variable, y hat. And you can see here there's an equation, scatter plot for F-150 trucks. Each data point represents the miles on the odometer and the price of the truck. And so you can use that to predict. So how can we predict? So the question was, the equation of the regression line is this. So this is my preferred way of writing the equation. Instead of writing y hat, the equation that was given to you by your calculator or by the question, it's great to write in parentheses. I usually write in parentheses, price hat, the predicted price is what that means. And then instead of x, just put in parentheses miles driven. I know it's kind of weird to look like a variable, but miles driven is your x variable there. And it's much easier to answer questions when you have it written like that. So it says, if we use the model to predict the price of a Ford F-150 with 100,000 miles driven, where should I put in the 100,000 miles? Where should I plug that in? Wherever miles driven is. And so you plug it in and you get your answer of 21,967 is our prediction. A common mistake I see in this section, sometimes students will only try to use the graph to predict this. You could look up 100,000 on the graph and say it's maybe around between 20 and 25,000, but it's hard to get an exact value there. If they give you the equation, always plug into the equation. Only use the graph if that's all you have. If you don't have the equation, I would use the graph. What is extrapolation? So you may notice, let's look back at that example for a second, and we'll come back to extrapolation. So 100,000 is kind of a blank spot in the data. There's no real data there, so we don't have actual data to support this. We're really using the trend line or the regression line as a prediction tool to say we think that 100,000 will be wherever the prediction line says it's going to be there. That's our prediction. And so that's called interpolating in between the data. So and that's pretty reliable. Like if you have a trend line and it's in between all the X values you've got, that's great, right? That's good. Sometimes you're making, so on this last example, if we were predict the miles driven for 250,000 miles driven and predict the price, well, I don't think it's going to be that accurate. It could be, but it's definitely possible that when you try to predict the Y value with an X value that's way bigger or smaller than the rest of your data, that is a recipe for disaster. It's just not going to work out very well for you. It's called extrapolation, and we frown on that. Maybe if it's a little bit of ways, it's hard to say, but 170,000 I would feel pretty good about. That's pretty close to the data. About 250,000, that would be extrapolation. And they're both extrapolation, but I would be very wary of the 250,000 mile prediction that the equation would give us. So we typically don't like to make predictions that they're far outside the X value range. Okay, so here was the data from the candy grab activity. We added the regression line to the scatter plot. So you can see it has a positive slope. There's the equation for that. Again, I would prefer you to write number of starburst with a hat on it for predicted number of starburst. Instead of X, write handspan in parentheses. But that's okay. They wrote it like that. Andres has a handspan of 22. Predict the number of starburst he can grab. So you would plug in 22 for X and just type it in your calculator, and it's going to make a prediction. 32.46. It's okay that that's a decimal, right? Because we're finding kind of the typical or average prediction. On average, he's going to get about 32. Might be 33, might be 32, might be a few more, a few less. But we predict, our best guess is 32.46. It's okay that that's a decimal. That's not a problem. We only round really percentiles to the nearest integer. Everything else we leave at least to the tenths or hundredths. Mr. Tyson's young daughter, Michaela, has a handspan of 12. So like the last question, 22, that's right inside the x values there. That's interpolation, that's good. Michaela has a handspan of 12. That's way outside the range here, but let's answer the question. So you can still plug in 12 and get a prediction. We predict 4.16 Starburst candies when we plugged in. But the follow-up question is usually something like this. How confident are you in each of these predictions? Well, the first one was pretty confident, but the second one was extrapolation, not so confident, right? Because first one was in the interval, 22 is in the interval of x values, but 12 is way outside of it. Maybe a kid's hand is kind of built differently, has trouble grabbing or grabs more than we think. So that's just not a good way to estimate there. So residual is this. So I'm going to kind of draw it for you because it's kind of something you almost have to picture a little bit to kind of get the idea of. Say this is a regression line, and you have 1 point below and 1 point above that regression line. Those values are actual values. They're actual data plots, actual points from the data. Given that certain x value, let's just say the x value was 20 for this one and maybe 10 for this one. Given those x values, we could use the line to make a prediction. In other words, I might have predicted this point when x is 20 would be the predicted point. And the distance between those is called the residual. Since the residual is below, this is a negative value, so a negative distance, or a negative. The residual is negative, I should say. Again, when 10, we would have made a prediction that the value would be about there. That would be the prediction, but the residual is this longer distance here. And this is positive because the actual is above the line. So that would be an under prediction for 10. And when x is 20, that would be an over prediction. So we predicted over what the actual was. So those distances, those positive and negative distances. Okay, so there's a way to remember this formula, and you do need to remember it because it's not on the formula sheet. It's RAP. So residual equals actual minus predicted value there. So it's just a pretty simple formula, but you have to remember the formula. It's not on the formula sheet, so I recommend that. So the question is, look at one data point. That's the data point that says data point there. A truck with 70,583 miles and a price of 21,000 miles. So the predicted value, if you go straight above that red data point, it's where it hits the line. That's the predicted value, right? Which seems to be above it. To find the predicted value, you would have to plug it in, right? So you plug in 70,583. The predicted value is 26,000. Now, in my mind, this guy got a pretty good deal on a car because he bought it for 21,994, which is almost 5,000 below retail price, or below the price that was predicted there. So in this case, a negative residual is good for him if you're a buyer. If you're a seller, maybe not. So the formula is RAP, residual equals actual minus predicted. The actual was 21,000. That's what he bought it for, 994. The predicted price was 26,000. So it'd be 21,000 minus 26,000 is $4,765. So it's negative, which means he bought it at a discount in the context of the problem, I think. Returning to the candy scatter plot, find and interpret the residual for Andres, who had a hand span of 22. I think they're missing some information here. I think we had to know that his actual number of Star Wars was 36, I believe. So if we knew that his original was 36, we could plug in 22, get the predicted, right? 32.46, and then take the actual 36 minus the predicted to get a positive residual is 3.54. So I think it's that number. There's two numbers at 22. It's the top number there. So that's a positive residual because it's above the line there. And it's 3.54. So this person was able to grab 3.54 more Starburst candies than was expected or predicted there. So that's what it says, right? You're talking about just what does that mean? So now interpreting the slope and the y-intercept. So a very specific way of doing this, but again, remember A is the y-intercept, B is the slope. So it's different than y equals mx plus b. B is the slope in this form. I might write down this in your notes. So that wording there is actually pretty helpful to interpret. So if you think about the y-intercept is the predicted value when x is 0. And the slope is the predicted value of y changes when x is increasing by 1. That actually is very helpful to the wording of the interpreting of slope and y-intercept. Don't forget to use the word predict. So again, y hat means the predicted y. Oftentimes that's the part that students forget here. So interpret the slope in context here. So let's try to interpret the slope. This is how I do it, and maybe it'll help you. You have to recognize the slope there is 2.83. So 2.83, it's positive. I like to write it as a fraction. Remember, slope is rise over run, change in y over change in x. So this guy is going to be the y variable, which for this one was, what are you talking about? The candy one. Okay, so for this one, the y variable was, I think, the number of starburst. And the x variable was the handspan. Notice these are both positive numbers. That's going to make a difference in my interpretation here. So what I'd look at is, say something like every time the x variable, every time handspan is increased by 1 centimeter. So every time handspan is increased, because it's positive, 1 centimeter, we predict that the number of starbursts would increase, because it's positive, by 2.83 starbursts. See what they wrote. So they might have written it differently. They started with the predicted number of starbursts grabbed increases by 2.83 for each 1 centimeter increase in the handspan. Don't forget the predicted word there, right? So interpret the slope. So let me tell you how I do slope, or y-intercept. They mean slope. The y-intercept is the next question. Okay, so I like to write down the ordered pair for the actual y-intercept here. So that should be 0, negative 29.8. So 0, again, x was the handspan, and this was the number of starburst. Okay, so number of starburst. So what it's saying, the meaning or interpretation of the y-intercept is that when the handspan is 0, so when you don't have a hand, that would be strange. The number of starbursts you can grab without a hand is negative 29.8. That's also strange. So the question is, does this y-intercept have meaning? And I would say it does not. The y-intercept does not have meaning in this case. It's impossible to have a handspan of 0 centimeters. I would agree with that. It's also impossible to grab negative 29.8 starburst. You grab 0, but you can't grab negative numbers. Okay, we're done with the lesson. Let's just look at a couple problems here. So here's a regression line for this guy from living space to assessed value for a house. So the more square footage you have, the larger the assessed value in general. It's generally a positive trend there. You can see it's a positive association, moderately strong, maybe not that strong. There's definitely some outliers there, so that's interesting. Or some unusual points, I should say, that don't follow that pattern. So new house has 3,000 square feet. Predict the assessed value. So this one, I would say, is a very straightforward question. You just plug it in, right? And I love the way they wrote the equation there. That's my favorite way. Instead of writing y hat, they write assessed value, or the predicted. That's what that hat means, predicted assessed value. They plugged in the 3,000, they showed their work, and they wrote the answer as 213,000. And let's look at that. So 3,000 is, 3,000 is outside of the x values that go from 1,700 to 2,400. So Not super confident about that prediction, but we can make the prediction whether or not we're confident or not. Predict the assessed value of a house with 2256. So again, you're going to plug into the equation, show the work, get 186,000. 2256 is within the X values of the interval there between 1700 and 2400. So I'm pretty confident about that prediction. Doesn't mean it's going to be perfect, but I think it's a very good prediction. How confident are you? The first one, not so much. It's you know, you're extrapolating past the data, so it's kind of dangerous, maybe not that accurate. Next question. Here's a scatter plot showing body temperature and heart rate for 18 teenagers. So I'm guessing as the heart rate increases, you would expect the body temperature maybe to increase as well. Maybe you're exercising, or I don't know, but you think that might happen. Try to interpret the residual for the body temperature of 97.3. So I don't even see that on there. So it's a little bit off the graph, but not disturbingly a lot. Like that's just barely off. So I'm okay with. So we're going to make a prediction. So the actual value there of the Y value there is 97.3, right? Oh, heart rate is 70. Okay, so I was looking at the wrong thing. Heart rate is 70. That is within the data, so that's very good. So let's find that value that the predicted value is. So the actual value is 97.3. When you plug in, you get 97.6. So we over predicted a little bit, right? So the residual is negative 0.3. So your actual temperature was 0.3 degrees less than what we would have predicted the temperature would be. Interpret the slope of the regression line. So again, slope is rise over run. By the way, look at the equation. There's a minus up there. It's 1,131.61 minus 1.08. So times the pressure. So 1.08, negative 1.08. So if I'm doing this problem, I'm thinking to myself, the way I do it, I write it, so it's negative 1.08 divided by 1, because that's the same number. And so 1 is the minimum pressure. So every time the minimum pressure increases by 1 megabyte or 1 MB, millibars, the maximum wind speed decreases by 1.08 kts, or knots. Okay, let's see what they said. So they said predicted speed, so forth. Interpret the y-intercept. So let's talk about the y-intercept. So for the y-intercept, I want to kind of graph it out. So this would be 0, comma, it looks like according to the equation that's 1131. So again, this guy is the minimum pressure, and this is the maximum wind speed. So when the atmospheric pressure is 0, the maximum wind speed is 1,131 knots. I don't know if that makes sense, because I'm not positive, I don't know, I'm not a scientist, that the atmospheric pressure can be 0. I don't think it could be negative, but I'm not sure if it can be 0. Let's see what they said. Unless you're in outer space. So I guess it's possible to be 0 if you're in outer space, but here on Earth, that would be impossible. That's your end of your screencast today.